All right, so I've done some more research on a couple new airfoils that I was recommended by a subscriber. Thank you. I'm going to put your name in right here. Pop. Appreciate you reaching out and giving me some pointers. So it was the Selig S1223. I did some analysis on, and then I did a little bit more research and found that there's another variant called the S1223RTL. The RTL performed a little bit better, so I went ahead and did the analysis on the RTL variant, and I have plotted here the lift and drag at various speeds. I kind of tried to match the colors, so like reddish brown is the lift and drag at 120. The greens are at 90 miles per hour, the orange and yellow 60, and the gray and black at 45. So it has quite a bit of variation between speeds, so this might be really fun to control for in software. The peak downforce occurs at different speeds. So here at 120 miles per hour, we have a point where we get 190 pounds of downforce, 193. Okay, we didn't get very good resolution on the drag. It looks like it's a little off, but it's under 5 pounds of drag. Then we have an increase in drag and a decrease in lift right here as we go up an angle of attack past 7 or 8 degrees. And then we have down at 90 miles an hour, our peak downforce is right here at around, what is that, 18 degrees? So we also have the drag doesn't go up the same way or as quickly, obviously, as it does at 120 miles an hour, but it's only at like 5 pounds. So obviously there are different points depending on what speed we're at where we will get maximum downforce. So that's something that we'll probably build a lookup table or generate some sort of equation for the control system to use. So it can look at the speed and say like, okay, at this speed, my best downforce is going to be at this angle of attack. And so we'll create like a little chart that the control software can use to look up what the optimum angle of attack is for the speed we're at. And an airfoil like this is going to really benefit from having that active control. I was a little skeptical looking at the S1223, the non-RTL version, because it just seemed like the drag was so low across the whole thing that, let's see if I can actually pull that up here. Yeah, so you have the maximum lift, it just climbs up, and the drag climbs very slowly up to the maximum lift, and then drag spikes and lift starts to fall off. So, I mean, staying around here at, what is that, about 12 degrees angle of attack would kind of just be the most beneficial thing to do, right? But we do get a little bit more lift or downforce on the RTL variant, and the drag is a little higher. So this is just at 75 miles per hour. Like I showed you a second ago, I plotted it at different speeds to kind of characterize it and see what we're looking at as far as variation and stuff goes. So we really have a big climb from 60 miles an hour up to 90 miles per hour. So we're only getting around 70 pounds of downforce at 60, and then it almost doubles going up to 120, which is, no, almost doubles going up to 90. So increase by 50% in speed, you double the downforce. Pretty interesting. Obviously that's dependent on where you are as far as angle of attack goes. Yeah, interesting airfoil. At lower speeds, you don't really have much downforce to speak of, but the drag is also very low. So I do also have all of the other speeds I plotted here. I just went ahead and plotted a few. Let's go ahead and show the rest of them here. You see there's some weird stuff going on at 75 and 120, or maybe that's that's 105 and 120. So it gets kind of squirrely there. That'll be something I probably analyze a bit more. And then again, the Xfoil had kind of a bit of a difficulty simulating a few of these airfoils. So I expect this is kind of just a lack of data available. Some of them didn't converge, and I had to get it to iterate multiple times to get some points. So this might be just like a forced data point where it was like, that works. I don't really know how the algorithm works in that software, but given that this is really the only outlier that kind of crosses a boundary here, 120 miles an hour, I would guess that this probably is somewhere between 120 and 135, or 105 and 135, and it would continue the trend of these other ones. But something we see that's pretty interesting is this shift of the lift. From the higher speeds, you get more lift at a lower angle of attack. And then around, looks like 105 miles an hour is when it starts to shift backwards. And this is probably the reason that this didn't converge, is it had a very kind of a transient shift in the AOA between the 105 and the 135. So I bet 120 is somewhere around here, and then that's when it kind of shifts. There's probably some boundary layer characteristic that we see at 120, around 120 miles an hour, where things kind of get squirrely and then they kind of shape back up around 120 or 135 miles an hour. So this is going to be an interesting airfoil. It is going to be one that we're going to want to control a little more carefully with the control system, and we're going to want to chart this quite a bit more with some more resolution on the speeds to see kind of where that transition takes place. So right now, I think this is the airfoil that I'm going to plan on making. I have started work on looking at some of the mechanical parts and kind of mocking up or making just drawings of the structural assembly and how we're going to do that. So I'll be making probably a video on the structure here soon, just kind of outlining some of the ideas I have, how I'm going to mount it on the car and control it with the mechanical components. This week I plan on ordering a carbon fiber starter kit and just kind of practicing. Maybe I'll make some front canards for the car, just some smaller parts to kind of get the feel and figure out what I'm doing as far as the wet layup of the carbon fiber. That's where I'm at now. Looking at mechanics, looking at starting some carbon fiber wet layup work. I would like to also do the structural inside the airfoil out of forged carbon fiber. So I'll probably order a forged carbon fiber starter kit and then kind of experiment with making forged carbon fiber spars for inside the airfoil. And then I'll also figure out how to support the structure of it. I might use like a carbon fiber tube, or if it looks like just the airfoil itself with the spars will be able to carry the load, then, you know, we might not use a cross member. I'm not sure yet. So another shorter one today. I think the 1223RTL is what we're going to focus on. So thank you, this guy, for the suggestion. I really appreciate it. That's one of the main reasons I put stuff on YouTube, just to get input from people that know more than me. So again, really appreciate that. And then my next video, also looking at doing some coding today for the Forza Motorsport telemetry output. I've already started on a Python script that kind of pulls that out, and I want to be able to output the serial, or convert it to serial, output it to an Arduino that can control little servos, and that way we can have like a physical mock-up that sits on my desk, and I can race in Forza Motorsport and watch the airfoils, have a little camera set up recording that, record the footage from the Forza game, and see if the reactions are what we expect. So I think that'll be super fun. So look for that video if that interests you. The Forza telemetry output could be used for a lot of different things, not just this. I think putting like vibration motors in my chair that reads like tire grip and sliding and metrics like that would be really cool to kind of give me a little more feedback on how the car is working. So that'll be kind of a dual use part of this project here. I think that'll be really cool. Thank you guys for watching. Be sure to be kind to someone today, and I'll see you next time. Peace.